Next, we have Jim Sykes with Mira Variable Stars.
Well, good evening. We're going to look at the Mira class variable stars, and this is kind of how it's organized. So we'll just get started. Mira was the first variable star discovered, and it wasn't recognized as such. Notice that Fabricus saw it on August 3rd, and it increased by 1 magnitude on August 21st. And he watched it, and then it faded in October. And he thought, well, that's a nova, which was not unreasonable. Then in 1603, when it was bright, Bayer observed it and called it Omicron Ceti, and again it faded. And then in 1638, Hawarda actually watched it for a long time and discovered that that it had a periodic brightening. Came back, he determined the period, and so he gets credited for the variability. But Hevelius is the guy who gave it its common name in his little publication there, and it is Latin, they tell me, for wonderful. I don't speak Latin, so I'll have to take their word for it. Kind of do a little review here for people who aren't familiar with this diagram. The Hertzsprung-Russell diagram plots brightness or absolute magnitude against the temperature of the surface of the star. And we have a whole bunch of stars that go right through here, which is called the main sequence, and are stars which are burning hydrogen at the core. So those stars usually live a long time, and the smaller they are, the longer they live. The cool dim ones are down here, and we go up to the more massive stars and get the hot bright ones up there. When they run out of hydrogen to burn, they leave the main sequence, and some of them go up there and become Miras, and we'll talk about that. If you want to be a Mira variable, here's what you got to do. You got to have a long pulsation period. Nominally, you see it greater than 100 days. I've also seen it 80 days. I don't know of any fights that have broken out over the 20-day difference, but you never know. Anyway, it can be to 1,000 or more days. It has to change in magnitude visibly by at least magnitude 2.5. They are spectral type late M, S, or C, and that's not the M you see on the HR diagram, but M indicates they're oxygen rich, C carbon rich, and S is kind of carbon and oxygen are pretty close to the same. The biggie is they have to pulse in the fundamental radial mode, which means that the whole star has to expand all at the same time and contract all at the same time. There are stars that have different times in different layers that go in and out, and also stuff that goes sideways, and those don't make it. And they are located in the late part of the asymptotic giant branch. That's the AGB, the TP, the thermally pulsing asymptotic giant branch, and we'll distinguish that from the early asymptotic giant branch as we look at things. Okay, some additional details. Most Miras start out between 1.5 and 3 solar masses. It's not a requirement, but most of them do. For various reasons, if they start out at less, the envelope's not necessarily deep enough to support the fundamental oscillation. And if they're too heavy or too massive, other things get in the way and cause them to not be Miras unless they can lose a lot of mass in the red giant branch. So generally, they lose enough mass by the time they get to be up where they could be Miras. They lose enough mass that your typical Mira will be somewhere between 1 and 1.5 times the mass of the sun. As you might expect, the pulsation is responsible for the variability of the star, but not necessarily how you might think it, and we'll talk about that. Miras, as most red giants, have deep convective cells that bring mass up from the top or from the bottom and distribute it throughout the envelope of the star. And they are big. They have significant mass loss and dust production. So if you can see this, here is Mira when it's bright, and here is Mira when it's not bright. You can see this is a lot longer exposure, and if you came up here and looked real carefully, you'd see a little red dot right there, but it's kind of hard to see from back there. So here's our stats about Mira. It is a red giant. No surprise there. All the Miras are. It has about 1.18 times the mass of the sun. It had estimated when it was back on the main sequence, when it first started out, you'll see it abbreviated ZAMS there sometimes, zero age main sequence. About 1.5 solar masses, they think, and of course it lost a lot in the red as it went through the red giant branch. As it swells and shrinks, the diameter changes between about 330 and 400 times that of the sun, and at the same time, the surface temperature changes between 3,000 and 2,600 kelvins. The magnitude, it can vary from 2 to about 10.1. It usually doesn't. It usually runs somewhere a little dimmer than 9 and somewhere up around 3 or a little less. But I've seen it up at 2, and it's pretty neat when it's up at 2. Infrared magnitude doesn't change as much, can range up to about 2 magnitudes. Pulsation period, 332 days, very regular, you can see from the light curve here. And it's about 300 light years from us and is a binary system. It has a white dwarf binary that goes along with it about 70 AU away. Okay, some pictures. Here's Hubble with Mira and Mira B, and that's in the visible light, and here we are in ultraviolet light. The separation is only 0.6 of an arc second, and they think that Mira B is a variable or a white star, white dwarf. So here's a Chandra X-ray satellite picture, false color. The blue shows high X-ray intensity, and here's an artist's conception, which is probably not accurate. The Mira B is not close enough that Mira is going to overflow its Roche lobe like that. If it sends any matter that way, and it does send some, it's more like with the solar wind type accretion on the white dwarf. So it's not that dramatic. Here's a neat picture from the Galaxy Evolution Explorer. Mira is zipping along through the galaxy at almost 300,000 miles an hour. So it creates a bow shock wave here, you see. Notice that as it loses mass, and it loses a lot of mass, it's shedding about 1 Earth mass every 10 years. The mass is excited with the collisions with ambient hydrogen, and then it leaves a tail behind it as it goes. So it's kind of an impressive picture, I think. Okay, let's talk about what makes Mira pulse. It's called, it used to be called the, I believe, the Eddington valve, but it's now called the Kappa mechanism. And what happens is fully ionized gas or neutral gas pretty much is transparent to radiation. In this case, we're talking hydrogen gas, and the partially ionized gas tends to block radiation, and this is how it makes it pulse. When you have the layer of hydrogen at the right depth, as it heats up, the hydrogen becomes partially ionized, which absorbs more radiation and heats up. Then this expands, and it causes the whole star to expand. And then as it expands, the layer becomes cool, the ionized gas becomes neutral, releases heat, contracts, and we do it all over again. And it takes 330 days. It's a big star, so the winds are pretty ferocious inside, and that also helps the star lose matter. Here's a schematic I did to give you an idea of the star. Here's the sun. Here's the orbit of the Earth. Here's Mars. The hydrogen layer that the ionization zone is around 30 million miles thick. And here's the surface or the photosphere of Mira when it's contracted, and here's when it's at max size. And it goes out and in 332 days. So it's got to be pretty exciting. Outside the surface of the star, there is a molecular layer, contains a lot of different atoms and molecules, and the one that we're most concerned with is titanium oxide, and we'll explain that in a minute. But this layer expands and shrinks along with the rest of the star. And it is that titanium oxide layer that causes the variability in brightness, but not necessarily how you'd think. Because when the star is at minimum, the outer layers are transparent. It goes right through them, and you see the hotter, brighter layers. So it is at when Mira is near its minimum when it is brightest. And then when it swells up, these layers cool, the atoms form molecules, they block the sunlight, a lot of the visible, and the star actually dims as it gets bigger. We know that the star is still fusing and so forth because infrared doesn't change much. But the visual magnitude, of course, can change by up to about 8. So here's a little animation of it happening. Notice that it is bright when it's smaller and dim when it's bigger. Yes. No. We will get to that. Yep. Good question. Leads to the heart of the star. We'll look at that. And here it is, not in animation. We have the when it's minimum here, we have the lines of sight going right through it. At maximum size, minimum light, we have the sunscreen blocking it. So we now know why it pulses. We know why it varies. Let's look at how we get Miras and why they do what they do. So, as all stars, it starts down here on the main sequence, happily burning hydrogen. And to leap ahead and answer your question, yes, the sun can become a Mira. It probably won't, or if it does, it probably won't stay one for very long. And we'll look at why that is. Okay, after however many billion years, 10 or 12 billion years for the sun, less if you're up here, more if you're down here, we run out of hydrogen at the core. Well, when we run out of hydrogen at the core, the pressure outward ceases, and so the star starts to collapse. Well, that heats it up, and it gets hot enough that hydrogen in the shell lights off. And that, while it's doing, adds helium to this core that's already helium rich because all the hydrogen at the core made helium when it burned. Well, we're going to add more. Meanwhile, this makes the star swell and cool and move out here on the red giant branch. This can last, say, up to 1 billion years for the sun. Okay, here's our picture. We have a helium-rich core. We have a hydrogen-burning shell. We have helium being deposited, and the sun or whatever it is swells up to a red giant, maybe 100 times as big as it was. So here we go. As the helium at the core adds up and adds up, it gets more massive, it becomes degenerate. That is to say, thermal pressure cannot hold the atoms apart, and electron pressure now does. So the core is going to heat up as all this happens, and when it gets hot enough, about 100 million Kelvin, helium flash occurs. Well, you'd think that might blow the star apart, but it doesn't, because it is releasing a lot of energy. What happens is the degenerate core sucks all that energy up and becomes non-degenerate again. Here's a picture of all that happening. We have degenerate helium, hydrogen burning. We have core ignition, and it makes the core non-degenerate. And we now have the star shrinking and becoming hotter with hydrogen burning in the shell and helium burning in the core. And these are nice, calm burns. They're nothing exciting about them. But what happens is the star shrinks now and becomes brighter. You can see it kind of becomes maybe a red or yellow giant because we're moving this way on the HR diagram. And since it shrinks but becomes brighter and getting hotter, it's kind of horizontal. So this is called the horizontal branch of the diagram. So This helium now is producing carbon and oxygen at the core. The hydrogen shell is producing helium. So it does that for a while. Here's a picture. Helium at the core, hydrogen shell, big hydrogen envelope, and whatever else it has. Okay, so there's enough, at least with the sun, and varies, of course, with the mass, but there's enough helium here in the core to last 100 million years or so. And then it shuts down. Well, now what happens is the carbon-oxygen core contracts, becomes degenerate. Gravitational energy heats around the core, and we get helium shell fusion, which goes along with hydrogen shell fusion. And the star expands and cools again and moves on to the asymptotic giant branch. They call it that because it's kind of asymptotic to the red giant branch. Okay, so we're getting closer to being a Mira, but we're not there. Here's a picture of a red giant on the AGB. We have, again, carbon oxygen core, degenerate, no fusion, helium burning shell, helium layer in here produced by the hydrogen burning shell. This star can have it swells up again, so it can have a luminosity of 10,000 times that of the sun. So it is a red giant, but it's, to get to your point, it's not necessarily pulsing here, or if it is, they're weak pulses. Okay, so this can occur for 1 million years or maybe up to 20 million years. The star, again, is swelling and moving up on the AGB. It's becoming more evolved, if you will. So this is the early AGB as opposed to the thermal pulsing AGB. Okay, so we're moving on. Here's what it looks like at the heart of the star. We have the degenerate core. We have helium shell burning. We have hydrogen shell burning. We have a bunch of intershell elements produced by helium and carbon, and we get what they call S process elements, which is S slow neutron nucleosynthesis, where an atom will capture a neutron, go through beta decay, the neutron becomes a proton, and so the element moves up one on the scale, and this is where we get a lot of the heavy elements in the galaxy. So also out here above the hydrogen shell, remember we have the convective shell that carries stuff to the surface. So here's what's happening in the early AGB. Okay, this works fine for quite a while. 1 to 20 million years. I put 5 there, but eventually that helium shell runs out. It just turns off. No gas left in the gas tank. The hydrogen shell continues to burn and makes more helium. So here's what we got. This has gone out. Everything else still going. And this really signals entry into the thermal pulsing part of the AGB, because when we get enough hydrogen here, or helium, sorry, it's going to pulse. But we don't have it yet, and it may take 100,000 years to get it. When it does, this ignites explosively now because it's a thin shell, and sends a thermal pulse out through the star and turns off the hydrogen shell, because this expands the star. This moves out. The temperature for hydrogen burning drops below where it needs to be. And so this turns off, and the convective cells can now move inward and bring up these heavy elements that are in this area. And this expands the star and deepens the envelope and brings a bunch of carbon and so forth up here. It's called dredge up, or third, it's, to be specific, it's called third dredge up, because there's a couple of others that can happen earlier. We won't go into it. Okay, here is what happens in the thermal pulse behavior, which is what's going to make our Miras, in 1.5 to 3 solar mass stars that started out that way on the main sequence. Like I say, our first wait to get enough hydrogen or helium to light off can be up to 100,000 years. And notice the helium then will only fuse for about 800 years. You know, so what we have here is, with 100% of the time, the helium's only fusing 1% of the time or thereabouts. The hydrogen, 99%. But this helium fusion lets us dredge up a lot of carbon, a lot of other, those TiO molecules and so forth, oxygen, silicon, so forth. As it starts out, it's a shallow dredge up depth, and the pulsation is pretty irregular. These are where you get your semi-regular variables, your SRBs, your SRAs. And as we go somewhere around normally 5 to 7 pulses, we have enough material dredged up and enough envelope that we can get a fundamental pulsation behavior with the star, and that is the Mira phase. So it took us a long time, but now we're into the Mira phase, but we don't stay there too long, maybe a couple of 100,000 to 800,000 years. And then as the envelope goes off into space, we don't have enough envelope, it becomes chaotic, and we start exposing the core and moving on towards being a white dwarf. But here we are at the Miras. Like I say, it may become a Mira variable. Some little things can change it, but a lot of stars, maybe half of them, become Miras at this point. Okay, just to recap there, the thermal pulse can cause a star to double in diameter over several hundred years. Enriches the envelope with carbon and so forth. That's where your carbon stars come from. Thermal pulses lead to the mass loss and so forth. Okay, we're a Mira now, and Mira itself is expected to stay that way for another 100,000 to 200,000 years. Its envelope mass right now is about 6 solar masses, and when it loses about half that, it will exit the Mira phase. Mass loss continues till only the degenerate core and the planetary are left, and the core becomes a white dwarf, and that's the end of your Miras. Now, I've showed you this before, and I'm showing it to you again just so I can show you the next slide. This was our photosphere of Mira out here at minimum, at maximum. And here is the same thing I just showed you, but we've gone out and looking way back at a different word I want is anyway, we're looking at a different magnitude or wider view. There we go. Okay, here is the molecular TiO part I talked about. But outside that is the neutral gas and dust the dust formation zone. And we get a lot of grain condensation here. And then Out here, up to about 3.5 billion miles from the star, we have the neutral gas and dust envelope. And you can see some of that from that Galaxy Explorer picture. The space around Mira is really cluttered with dust and gas that it has lost, and it just fades to space out here. And one last thing, if you want to look at Miras, there's a lot of them out there. The General Catalog of Variable Stars lists over 6,000. It's always some up. They don't change quickly. You don't have to look at them every night. The AAVSO would love to have your observations. You can print out charts there and compare with your comparison stars and make an estimate, and they'd love to have it. Mira is a great one because it really it's the brightest. It gets up to about magnitude 2 sometimes. And another favorite of mine is R Leo because it's pretty easy to find. There's Regulus, and Omicron's pretty bright. A couple of key stars up here that you can track on at fairly high magnitude. And the nice thing about it, when it fades to down around 10 or 11, there's some nice comparison stars in here, and it makes a nice little triangle with these two stars. It's really, really easy to follow through its whole category. That didn't work out well, but anyway, another one that two I'll mention here. With T Hercules, what I like about it is it's short, 165 days. You can follow it through. And here is R Leporus, also known as Heinz Crimson Star. Even if you don't want to follow it as a Mira, you owe it to yourself to look at this star. It's a carbon star. It's blood red, and it is a fascinating star to look at. I have this slide with stuff in order as a handout for anyone that wants it, in case you want to take a look for the Miras.
That concludes tonight's presentations. Thanks everybody for attending. We're gonna gather outside and try to get in a little observing tonight. Thanks everybody for joining online, and we'll see you again next month.